Welcome to part 1 of Unit 3, which would be on controller design. So before we begin talking about design of controllers in this unit, we need to look at analysis. How do we analyze the behavior of the controllers that we will design, or the closed loop system that we will incorporate, within which we will incorporate the controller? So for that, we will use a tool called root locus. We'll look at how the root locus can be used to analyze the closed loop behavior of a control system. We'll look at the properties of the root locus itself. We will then proceed to look at how we can sketch, or to get intuition about sketching the root locus, as much as these days computers are widely available to be used in order to automate the sketching of root locuses. And then we'll conclude this section by looking at the PID controller, just as an overview of what the PID controller is and what it's capable of, and how can it be designed. And then in the latter section, which is part 2 of these lectures, in another video, you will look at the other sections talking about design specifically for state variable systems, and specifically we will look at state feedback control and the system properties of that can lead to us being able to design a system, or a control system, or a state feedback control system. So we have seen in previous chapters that the roots of the transfer function being located on the left half plane of the left half plane of this plot would mean that the system is stable. We have also seen that we have also got an appreciation of the fact that stability is not always the only concern when designing control systems. The second most important concern is to meet performance specifications. We have seen, for instance, that in a second order system, you can talk about performance specifications in terms of rise time, peak overshoot settling time, and the likes. So performance specifications have to be met, and performance specifications are important. We have got also the appreciation that these performance specifications are also dependent on the location of the poles in particular, as well as affected by the location of the zeros within your S-plane. So the root locus in itself would be used as a method of analyzing these locations and see what happens for different setups of the feedback control system. Consider an example below. We have a negative feedback loop with a proportional controller here, Kp, or a parameter, or a controller is simply K, whereby the controller simply amplifies the error signal and feeds it into the plant control. So let's say we have a first order system. In this case, our G of S is a first order system, which is 1 over S. Now, if you do a calculation, you'll see that your closed loop system then becomes K divided by S plus 1 plus K. So this will become the closed loop transfer function from U to S. Now, having seen this, we will also observe that now the closed loop pole, or the pole of this transfer function, would be S is equal to negative 1 minus K. Negative 1 minus K, in the sense that this is going to be where the pole is located, and this location of the pole depends on K. If, for instance, we let K become 0, right, which means this is 0, which means basically effectively we are cutting this into an open loop system. So you're cutting off this. The pole will be located at -1. So the pole of the closed loop system will be equal to the closed pole of the open loop system. It will just be located at -1. Now, as k increases, we see that the pole will also increase towards the negative. So at one point it will be here, it will be k, it will be -1 minus k, -1 minus 4, -1 minus 10, which is -11, -12, -14, and so on and so forth. And then it will go to the negative infinity as k goes to infinity. So this sketch, the thick black line here, shows the locations, the different locations of the pole as k increases from 0 to infinity. And this sketch here, we call this the root locus of the system, because it shows the path, or at least the locations of all the closed loop poles as k increases from 0 to infinity. Proportional gain, on the other hand, let's look at the proportional gain in terms of second order system, how it will behave. So let's say we have a second order system, and this system is of the form, it's of the same form whereby you have a proportional gain as a controller, and this is the plant transfer function. So the open loop plant is, it's of the second order, so it has two poles, and these poles are going to be located at s is equal to -1, s is equal to -2. So -1, they are shown by the axis here, and -2. These are the poles. Now, what happens in this instance is that the closed loop, if you calculate the closed loop transfer function, you will find this transfer function, so it will be k s divided by s squared plus 3 plus k s plus 1. The closed loop poles, if you use the quadratic equation, will therefore be 2, and these roots of this quadratic equation are going to be P0, which is given by that, and P1. So this will be the closed loop poles. Now, if you look at a closed loop pole P0 and take it for k is equal to 0, let's say k is equal to 0. So when k is equal to 0, this becomes 0, that becomes 0. Here you have square root of 1, which is just 1. And then here this becomes 0. So you have -1 plus 1, sorry, -3 plus 1, which is -2. -2 divided by 2, that will give you -1. So this would be the location of this particular pole. And then P1 will be the location of this particular pole. Now, if you look at what happens as k goes to -infinity, you will see, in fact, if you use these two equations, you will see that as k goes to infinity, this pole P1 will tend to go, its value will tend to go towards the negative infinity. However, this pole, this particular pole P0 will tend to go to 0 as k goes to infinity. And this again, we call these thick lines, these two thick lines, which shows the path of the closed loop poles as k goes to infinity. We call them the root locus. What's important here to note is that one, which is not coincidental by the way, that one of the poles goes to a 0. It goes to a 0. It goes to a 0, and then the other pole goes to the negative. Because remember, this is the closed loop 0 here, it's located here at 0. So one of the open loop poles goes to the closed loop 0. It's very important to take note of that. So now, by definition, we define then a root locus as a set of all closed loop pole values for all the values of k varying from 0 to minus infinity. And we call this equation 1 plus k gs equal to 0. We call this the characteristic equation because this equation is the equation that gives you the location of those closed loop poles. How is that? For instance, look at this. If you have your g of s is equal to the numerator divided by the denominator of s, you will notice that you can write the closed loop transfer function at the bottom of the closed loop transfer function. The denominator will be d plus k plus k times n of s is equal to 0. This would give you the equations of the closed loop poles. Now, because of that, this is basically the transfer function, because if you divide by d of s on both sides, you end up getting this characteristic equation. So this characteristic equation gives you it summarizes basically the paths, the path of the of the closed loop poles as k varies from 0 to infinity. So let's take an example here just to clarify what I'm saying here. So if we have a transfer function g of s which has on above, it has these zeros. The zeros are located at -6 and -4, and then it has two poles which are located at -2 and -1. Now, if you calculate the sorry, if you calculate the root locus using these commands, first you load the control system package into Octave, then you calculate the transfer function, then you calculate the root locus. You will see that the root locus will be this blue line, and this blue line will show you, for instance, that the open loop poles, these ones, the bottom of this, the root locus starts from here, from the open loop poles, which is -1, -2. Because when k is equal to 0, then the poles of the closed loop are simply given by dn of s is equal to 0, because k times n of s, this will be 0. Right? And then then as k increases, what will tend to happen is that this one will go this way, and that one will move to the left. They will meet here, and another one will go up, the other one will go down, and then up until they reach this end, whereby one of them will split to go to another 0, the other one will split and go to the other 0, which is located at -4. So you see here the two zeros are located at -4 and -6. And this is a very common behavior of a root locus, that as k goes to infinity, the open loop poles go to the open loop zeros. To assist in sketching the root locus, these are some of the properties that you will see that the root locus observes. So the first property that we'll look at is symmetry. So in terms of symmetry, the root locus will always be symmetric about the real axis. What this means is that this part of the real axis, the bottom part, and the top part of the real axis will be mirror images of each other. So if you look at this root locus, you'll see that there's a line here, and then you have a ball, you have a semicircle on top of the on top of the real axis, and this semicircle will also have a mirror image at the bottom. This is another example of a root locus. The same thing applies here. You have this arc in a line. At the bottom, you also have an arc as well as a line. So that's the first rule. The root locus will always be symmetric about the real axis. And then the location of the root locus on the real axis. So the rule is that the root locus will always be on the left, towards the left, which means if this is your axis, it will always be towards this side, towards the left of an odd number of poles and zeros. So if you look at this particular root locus, for the root locus on the real axis, what we are saying is that it will always be on the left of an odd number of poles and zeros. So you have a pole here, and on its left, you have one pole. On its left, you will have the root locus, this portion. Let me show it in green. So you'll have this portion here, because it's on the left of one pole. Here you have two poles. On the left of two poles, because this is even, you won't have a root locus. This side, on the left of three poles and zeros, you will have a root locus. The same thing applies here. You have 1, 2, 3 poles and zeros, which means the root locus will be there for the whole of this real axis. So one important rule, the root locus is always on the left of an odd number of poles and zeros. Another important point is what's called the breakaway points, or break-in points sometimes. These are the points where the root locus leaves and enters the real axis. What do we mean by that? We mean points like this. Let me use a turquoise marker. It means points like this, where the root locus is on the real axis and then it breaks away into the imaginary axis here. And then you have here as the break-in point where the root locus was moving from that, and then it comes into the real axis. So this is the break-in point. This is also a break-in point here. And the way to calculate the break-in point is by solving the following equation. If you imagine that the open loop transfer function will be g of n of s on top, d of s at the bottom. If you solve this equation, n of s derivative of d of s, n of s times the derivative of d of s minus d of s times the derivative of n of s. If you solve this is equal to 0. If you solve this equation, you will find a lot of points s that satisfy this equation, and those points, some of them are going to be the break-in and breakout points. Another important piece of information that you can calculate is called the angle of departure or angle of arrival. And the way it works is that the angle of departure is when the angle at which the root locus leaves an open loop pole. So here, for instance, you see we have an open loop pole here, and then this angle here, theta, is called the angle of departure. And then the angle of arrival is the angle at which the root locus enters 0. So remember, these are going to 0. So sometimes you will find that a root locus will enter into a 0, and that angle where it enters a 0, that angle is going to be called an angle of arrival. Now sometimes you may need to calculate the value of the poles at a specific values of k, and for that to happen, you simply substitute your value of k into the characteristic equation depending on how you write it. So if k is equal to 2, you simply write 2 and then solve this equation. Then that gives you the value of k, the value of poles at the specific value of k. Another way is to calculate the point at which the root locus cuts into the imaginary axis. And sometimes that the best tool to use in that instance is called the Rothowitz criterion or the Rothowitz method. But so generally, to recap, you have the following properties: that the symmetry, the root locus is symmetric about the real axis. On the real axis, the root locus is located on the left of an odd number of poles and zeros. The breakaway points can be calculated and the breaking points. And generally speaking, the root locus moves in such a way that the locus moves from poles all the way to zeros as k goes to infinity. So just to emphasize on one last property of asymptotes for the root locus is that these points, or at least these lines, which we call asymptotes, which we can also aid in the sketching of the root locus. And asymptotes are basically the lines which the root locus approaches as it elongates, as it goes as the pole get bigger and bigger and bigger and bigger. So for example, typically when you draw a root locus, we know that the end poles go to the m zeros, and then the remaining number of poles will go to infinity. So let's say here in this instance you have 1, 2, 3, 4. You have four poles and then 1 0, which means your n is equal to 4 and m is equal to 1. So now what happens is, as the root locus, as k goes to infinity, the one pole will go to a 0, and the rest of the poles will go to infinity. This one will go all the way to be infinite, negative infinity. This one will go all the way up above into some positive infinity, and so on and so forth. So the asymptotes gives us the lines, or at least the angles at which the root locus will approach as it goes to this infinity. For instance, in this case, we have one asymptote here. As it goes to infinity, it will tend to follow this horizontal line. So the horizontal line here is an asymptote. As it goes up here, this one, as it goes up towards the top left, it will approach this asymptote, which is shown by a dotted line, and a dotted line here. So we can, in fact, at this point calculate the center of this asymptote, which is sigma a, and the center sigma a is simply calculated as n, which is the number of poles, minus m, which is the number of zeros. In this case, we have 4 minus 3 is equal to minus the sum of the poles and the sum of the zeros. So it's equal to that divided by the sum of poles minus the sum of zeros. That will give you this point, this particular point here. So this point can be calculated using this formula. And the angles at which this asymptote leave, so in this case, in our case, we have an asymptote located at some convenient point there. And then we have one asymptote going this way, another asymptote going that way, and another one going that way. Now, if you calculate the angles, if you calculate this angle, that angle, as well as, so this will be the second angle, the third angle, because you have 3 asymptotes, and then this other angle. So all of these angles, in this case we have n minus 1, we have n which is equal to 4, we have m which is equal to 1, because there's only one pole, n minus 1 is equal to 3. All of those 3 angles, angle phi A1, A2, A3, all of those angles can be given by this formula, where k is equal to the difference between, it's equal to 0, 1, 2, and so on and so forth, up until n minus m minus 1. In this case, in our case, this will stop at 2. So it will be for k is equal to 0, k is equal to 1, and k is equal to 2. So we'll have those three angles here. Let's go over how to then calculate how to then sketch our root locus. So there are a couple of rules that we can use when sketching the root locus. The first one is, so the steps that we might take will be, the first will be to plot the open loop zeros and poles, and then remember we can draw also the root locus on the real line, because remember we said it's going to be on the left side of an odd number of poles and zeros. So it's going to be on the left. Now, so that we can plot quickly. And then if need be, sometimes you may need to draw your asymptotes and then find potential breakpoints, that is break in and break out points, and then try basically necessarily to put it together. So you may also calculate where the critical points, such as where the root locus crosses the imaginary axis. The point, for instance, the angles of departure and arrival. And you can use the fact that for second order systems, the root locus will have a circular axis. So the root locus on the sketch, the arcs are going to be circular. So let's tackle now the first step. Step number 1. So we look at the poles, the zeros. On the zeros, we see, you can say s plus 4 is equal to 0, which implies that s is equal to, that is our first 0, is equal to minus 4. Right. And then for the poles, we have s squared plus 2s plus 2. We see that we require a quadratic equation. We can solve these poles because this is going to be minus b, which is 2 divided by 2a plus or minus square root of 2 squared minus 4 times a, which is 1, times c, which is 2. So we have that, which means if you calculate this, we get minus 2 over plus or minus square root of, so this is 4 minus 8, which is negative 4, over 2, which is equal to minus 2 over 2 plus or minus, so this is the square of negative, the square root of negative 4 is j is 2j. So in fact we have negative 1 plus or minus j. This would be the conjugate pole pair. So it means then around here in minus 1 we have 2 conjugate pair poles here, and then the 0 would be located around minus 4. So we now need to tackle, okay, so let's say now we tackle the second step, which is draw the root locus on the real axis. So we count on the left hand side of the what, of an odd number of poles and zeros. So this is this. So there will be a root locus here as well. So at this point we know that somehow these poles must go to this, one of the poles must go to the 0, and we also know that somehow this poles must end up on this line. So we know that one of these poles must go to a 0, and somehow these poles must all end up somewhere in this line. So we look at the third step, we say draw the asymptotes. We don't necessarily need, okay, first of all we can see one of the asymptotes is that this is going to go to infinity. but you don't need to draw the asymptotes, but you can look at the breaking point. So since we know this has to join somehow here, we can look for a breaking point. That's a potential for completing the root locus. And then we look at where they cross the imaginary axis. That is, imagining maybe this pole somewhat is circle around here. And then we find angles. We can find angles of departure. You can also use the fact that for a second order, because this one is a second order system, the arcs are going to be circular. So somehow the poles, the arcs on the poles, whether they go that way or that way, they're going to be circular. So let's move on and try and look at the breakpoints. Yeah, so if we wanted to calculate the asymptotes, there are two things that we can calculate: the center of the asymptote as well as the angle of asymptote. So for the center of the asymptote, we can calculate that we can sum the poles, negative of the poles. So we sum minus P1 minus P0, which is going to be 1 minus J, plus minus P1, which is 1 plus J, minus the sum of all negative zeros minus negative 4, right? So we sum those. We say minus the negative of the 0, so this becomes positive 4, and divided by n minus m. N is the number of poles, m is the number of zeros. So this gives us 2, because the j's will cancel out, minus, so it's 2 minus 4. And then divide by 1, which is negative 2. So the center of our asymptotes is going to be at minus 2. So we need to show what the asymptotes are, the angles. So calculate the angles, phi A. Because the angles are calculated up to k minus n up to k is equal to n minus m minus 1. This is 2 minus 1, which is 0. It means we only have one calculation of an asymptote, and so we will have and the angle here will just be 2 to the power, we substitute the k of 0 plus 1 divided by 2 minus 1 times 180, and then this gives us 1 over 1 times 180 degrees, which is basically 180 degrees. So we have then our asymptotes would be at this angle of 180 degrees. So which means finally the poles have to lie on this asymptote. For completeness, let's just calculate the angle of departures. So we know from our previous assessments of the root locus, the properties of the root locus is that the angle of the root locus is negative 180 degrees, or at least the angle of the root locus is multiple of negative 180 degrees. Now, therefore means that we can say the angle of the zeros, which are positive in this case, the angle of the root locus, which is minus 180 degrees, is equal to the angle of the zeros minus the angle of the poles. So in this case, we only have 1 0 and 2 poles. So we'll say, therefore, the angle of the 0, which is positive, minus the angle of the first pole minus the angle of the second pole is equal to negative 180 degrees. Now, which means, therefore, it means we can calculate, therefore, the angle of departure at pole number 0 is simply equal to minus 180, subtracting the angle of pole 1 with adding the angle of 0. which means we can say, then we can confidently say now the angle of departure here at pole number 0 is equal to 180 plus the angle of 0 with respect to the pole number 0 minus the angle of pole number 1 with respect to pole number 0. Now let's look at angle of the 0, and the angle of the 0 here, remember we said we are calculating it with respect to pole number 0. This is P0, which is this one, that's P0. So this angle is the angle of the 0. So the angle is always calculated from the line that's parallel to the real line. So this angle, as it stands, it's equal to, you will see that this angle is from a triangle. You can see that this forms a triangle here, a triangle like this, where the height of the triangle is 1, and then the length of the triangle is from -4 to -3, which is 3. So this is basically a tangent inverse of 1 over 3, which is equal to 18.44. Right? Now, what that means then is that we have now this one. We have now this piece. We look at the angle of P1 with respect to that. We look at the angle of P1, so this is P1, and then we can see this is the angle. So clearly, without calculation, we can see that P1 is actually perpendicular. It's a 90-degree angle because it's immediately below P0. So we have P1, and that angle is 90 degrees. And so we can calculate, therefore, the angle of departure, 180 plus 18.4 minus 90, which is equal to 108 degrees. So it means now, when we cancel all of this, canceling all of this, it means now we know what the angle of departure here is. So the angle of departure will be around that. So this one will be our angle of departure, theta d, which is 180 degrees. So we can do the same also here to find the angle of departure of the second pole, P2. Let's do that. Back to our problem. We see that then we have just found, so we have plotted the open loop poles, drawn it on the real path, and then we have just calculated the breakpoint here. So we have just found out that this is going to be a breakpoint where the root locus starts to leave or enter the real axis. So it means from here on, the root locus will be leaving like this. So since we know these are circular, we can almost always complete this way. And so we can draw that these poles will shift that way, and one pole will shift that way. And we know that one of the poles will move to the 0, whilst the other one is supposed to go to an infinite number of poles somewhere in the infinity. So this then, it's how we conclude sketching the root locus in this example. So the sketch that we have just done can be verified using a computer. In particular, we can use the control toolbox in Octave. And what we see here is that if we use these commands, we load the control package and the transfer function and plot the root locus, we see that the root locus will move from these two poles, and then it will move to the 0 and the 0 in infinity as per the sketch that we have just produced. So what other interesting question that we may answer now that we have figured out the root locus would be, for instance, what is the value of k? What is the value of k, or what should the K parameter be set to, so that the closed loop poles are all equal. Now we have done an analysis to show that the closed loop poles would be equal when they all reach this break-in point. So the break-in point, in fact, we have just analyzed that it's by calculating the numerator by evaluating the numerator at the break-in point multiplied by the denominator of the transfer function at that break-even point minus the denominator, the break-in point, times the derivative of the numerator and the break-in point. So if this is the derivative equal to 0, by doing this we can calculate the break-even point, which we have done earlier, to indicate that this break-even point is minus 8. Now to find the value of K when both poles are equal, we then means that both P0 and P1 would be equal to minus 8, which means if we take the equation of the root locus itself, which is 1 plus K G of S, which is equal to 0, which implies that 1 plus K times S plus 4 over S squared plus 2S plus 2 is equal to 0, and we substitute S is equal to minus 8. This would imply that we have minus 8 squared plus 2 times minus 8 plus 2 plus, so this is the denominator here, this is the denominator, which is this, plus the numerator K times minus 8 plus 4 is equal to 0. Now if we take all of this, let me draw a line here. So therefore it means we have 64 minus 16 plus 2, and then here we have 8 minus 8 plus 4, which is negative, and negative 4K is equal to 0. So if you take that, which implies that so effectively 64 minus 16 plus 2, that gives us 50. 50 minus 4K is equal to 0, which is a good implication that our K is equal to 50 divided by 4, which is equal to 12.5. So this becomes our value of K. So if we want the closed loop poles to be both equal, then we will place it at K, which is, our K has to be 12.5, right? That's what the equation says, and then we can calculate therefore, which means we can also attempt to answer the question, what is the settling time? So the settling time, obviously here, since the poles were going to be real, settling time is like a first order system, and the settling time here, TS, would be approximately equal to 4 over the value of the pole itself, which would be so this would be the value of the pole itself, and then this would be 4 over the value of the pole, which is 8, and then which means that our settling time is roughly around 0.5 seconds. Another interesting question might be, what would be the value of K when the closed loop poles are located at this particular location? So assuming that in this case we can see for sure that there is a point where the closed loop poles are located at this conjugate poles. For instance, in this case here, we say one of them will be located here, the other one obviously around here at the opposite side. So we can use this equation, the characteristic equation here. We know that this is the case, which means we can say, for instance, that kg of s is equal to -1, which implies that k can effectively be equal to -1 over g of s. In fact, we can see that the magnitude of k, that is the size, because we know k has to be positive, has to be equal to the magnitude of this. So this simply implies that we need to substitute one of the poles. So we need to substitute, say, for example, in this case, we can take this one s equal to -3 plus 3i into this value, and then we can calculate what the value of k is. So this means that we have the magnitude of, remember this is the opposite of that, which means the magnitude of s squared plus 2s 2 over s plus 4, which is the 1 over ek. It's negative, but it doesn't matter because the negative, as long as we have the magnitude, we know the value that comes out of here is going to be positive anyway, so we don't need to insist on the negative value. So we can substitute that. We will get, here we have, we will have -3 plus 3i squared plus 2 times -3 plus 3i plus 2 all over s, which is -3 plus 3i plus 4. So this gives us, at the bottom, we have the magnitude of 1 plus 3i. On top, if you work it out on top, then you would have the magnitude of, so this would give you -4 minus 12i. If you work that one out, for brevity I will not do that, but you can work this out. This will work out to that. So we want to find the magnitude of that. Let's multiply by complex conjugate on top and above so that we can make sure that the bottom here, it's a real number. So we multiply by complex conjugate, which is 1 minus 3i, and then at the bottom 1 minus 3i times this -4 minus 12i plus 1 plus 3i. This gives us at the bottom 1 squared plus 3 squared. On top it gives us -4, and times that minus 12i plus 12i, times that minus 36, which gives us, at the bottom it's 10, this cancels that, minus 36 minus that minus 40, and then, which means we can therefore say the value of k is equal to 4. Another interesting bit of analysis that can be done, which is of a similar sense, is, let's say we want to find out the value of k for when the damping factor is 0.9. Now we know from the analysis of the second order that in fact on this axis the angle at which the damping factor is related to the angle at which the pole is located. So in fact theta is equal to cosine inverse of the damping factor. In this case, this would be, the damping factor 0.9 would get around 25.9 degrees. And so we can initially simply take if this axis were all equal, that is the distance here, the distance of one unit is the same as, if 5 units this way, if 5 units this way is the same as 5 units that way on our graph, we can simply take a paper and then with a protractor just draw theta here at this angle of 25.9 degrees, and then we can be able to calculate to find out what this point of what is the value of the pole at that point where they intersect, which is this point. However, sometimes you will see that like in this instance, our root locus plot, which is computer generated, does not have an equal scale. So in this case, we can alternatively decide that, for instance, we know that this would be, so the angle would be in the form of a right angle triangle this way. So we know that 20, so if our theta is 0.9, this simply means we have, sorry, if our zeta is 0.9, this simply means if we have the cosine here, the cosine of theta is equal to the opposite, sorry, the adjacent over the hypotenuse. So which means we have roughly 1 here and 0.9 here. If we take it using simple trigonometry, cosine of theta is equal to hypotenuse, which is 1 here, and then the adjacent, let me just use a different marker, which means if this length here is 1 of that right angle triangle here, then this one would be 0.9. And we can try and triangulate here what this point should be here, so that we can plot it on our root locus. In fact, here we know by Pythagoras theorem we can have, this is the square root of 1 squared, hypotenuse squared minus 0.9 squared. This would be that length, and then if you calculate this, it should give you around 0.44. So we know 0.44. So we know that the point or this line can be drawn with a slope of, if we are looking at the real axis here, JW, no, the imaginary axis versus the real axis, which is sigma, we can have a ratio of sigma to JW, which is the real to the imaginary axis. We can have 0.9 here, and this side, the imaginary axis, it will be 0.44. In our case here, we can have a clear point here at 5, say for example. If this side is 5, what should be the corresponding point here? If we do a cross multiplication, you will find out that this point that should be here, corresponding to the same ratio, should just be around 2.4. So a point 5, 2.4, 1. So this is 1, 2, 3. So this should be 1, 2.4, which is around here. So this is the point that makes this angle. So we take a straight line and try and triangulate that. So it should cross at this point. That should be a point where it crosses our root locus. So which means we are looking for a value of k when the poles are located here. And obviously, since it's located here, the other one will be located as a conjugate complex pole here. So we can do a simple scaling by trying to measure what would be, roughly speaking, what would be this distance here. That is this distance. And then, roughly speaking, what would be that distance, that side. So if you do that, you will see that your point comes roughly to minus 5.6, plus or minus 2.6i. So that would be like this point. So this question is the same as asking what should be the value of k whilst the poles are located at this location. So the question now simplifies, because you have already calculated the value of k's knowing or given the value of the pole. It means we can tackle this. So just to go over the procedure again, or at least the logic that we have followed, we said, what is the value of k when the damping factor is 0.9? We can quickly calculate that. This means on a triangle, we know the damping factor of 0.9 simply corresponds to a certain angle. And that angle we can find by simply using, either we calculate the angle this way by cosine inverse and we draw it if our plot has equal scales. If it doesn't, we can just simply draw a right angled triangle here and try and estimate what would be the real axis length versus the imaginary axis length of that small triangle that we can draw here. In fact, we can expand that triangle to a value that we know using the same ratio here. Instead of just taking 0.9, we can expand it using 5. We can expand this same ratio to the values that we might be easy for us to plot, which is like 5 versus 2.4, and extend that up until it touches the root locus. Then we get the location of the pole there, the root locus. In this case, we get 5.6 plus or minus 2.6. Now this means now that we have our P has to be equal to minus 5.6 minus 2.6 I. We can take that and try and calculate K. So K becomes the magnitude of 1 over GS, which is, in this case, we can take this point minus 5.6 minus 2.6 and square that plus 2 times minus 508 minus 5.6 minus 2.6 and plus 2, and then we have at the bottom minus 5.6 minus 2.6 I plus 4. This means that we can take this square here. Let's just take it here. So 5.6 minus 2.6 squared minus 5.6 minus 2.6. This is equal to, multiply this, we get 31.36. We get plus 5 times that is going to be plus 14.56 plus 14.56 I each time that this one 2.6 I multiplied by 2.6 I, that's going to be positive, negative, because it's going to negative times negative is negative, and then I times I, which is negative as well. So it's going to give us a negative 6.76. And then adding all of this up gives us, it gives us 24.6 plus 24.6 plus plus what, 29.12 I plus 29.4, which means now we can go back and say we take that 24.6 plus 29.12 I minus 11.2, which is 2 times 5.6, minus 5.2 I plus 2 divided by 5.64. This is negative 1.6 minus 2.6 I, and then this gives us, if you do the multiplication, you'll find that you get 15.4 plus 23.92 I minus 1.6 minus 2.6 I, and then 1.6 squared plus 2.6 squared. If I multiply this, for instance, if I multiply this by complex conjugate, so that I remove the I on the bottom and the top, I remove the I at the bottom, And then if I do that, then I have this the following. I have minus 86.83 plus 1.77 I, and this gives me 9.32 over minus 86.83 plus 1.77 I. Now if you take the magnitude of this should give us, remember when you take the magnitude of the complex number is like the square root of the real part squared. This is just wrong. Plus 1.77 squared over 9.32, and then the magnitude therefore becomes, if you put that into your calculator, this gives you 86.85 divided by 9.32, which is roughly speaking 9.3. So the value of K for 100 damping factor, so that the damping factor of the closed loop system can be 0.9, is actually 9.3 K. What is roughly about there, because the way you extrapolated the point here would reduce the accuracy of your calculation. In the sense that this point might not exactly be the 5.6 plus 2.6 I, as you might later discover, but this can give you roughly it's roughly how you can use then the root locus to do this calculation. So let's consider here an example for the state space system, and in this example we just need to find the characteristic equation of the model, sketch the root locus, and find the values of K for which the model is stable. So what we will do is to proceed first of all by looking at the transfer function. Remember that the transfer function of a state space model can be obtained using this formula. Now, knowing this, we can see that first, if you need to calculate this part of the equation, this is S0 minus 0 to minus 0.5K minus 1, 3 minus K, which means we have, in this instance, S and then 1, and then minus 2 plus 0.5K, and at the bottom we have S minus 3 plus K. Now, if we take the determinant, this is equal to the main diagonal, we multiply it out, this will give us 3 minus 1 times that, this is plus 2 minus 0.5K. Now the inverse of Si minus A, inverse is going to be 1 over times negative of that, to negative of 0.5K. Yes, so you swap the main diagonal and then you negate the other diagonal. Now if you calculate the transfer function G of S, it's going to be equal to C, which is 0 minus 1 times Si minus A inverse times B, which is minus 1, 0, plus 0. Now this gives us, if do multiplication, remember we have 1 over Si minus A times, so we do C times this inverse, which is that C. We're going to have, in the first instance, you're going to have 0 times S, 0 times S minus 3 plus K, which is 0 plus negative 1 times this negative 1, which is going to give us 1. And then we have the other, which is what? We have another which will give us this S minus S, and this will be times 1 over 0 plus S, like that. And then if we work out this, then we see that we're going to have on top times 1, which means we have, therefore, okay, let me write it, therefore we have 1 over S squared minus 3S, oh okay, this is a mistake here, plus KS plus 2 minus 0.5K, something like that, which is our transfer function. Now from the transfer function we can say the characteristic equation here is S squared minus 3S plus KS plus 2 minus 0.5K is equal to 0, which implies that we have S squared minus 3S plus 2 plus K times S minus 0.5K, 0.5, not K, because it's not K squared, which implies that we have, if we see this grouping here, we can divide both sides by S squared minus 3S plus 2, we get 1 plus K times S minus 0.5 all over S squared minus 3S plus 2 is equal to 0. So this becomes the equation that we are going to use to draw our root locus. So if we express this characteristic equation in this format, we can begin now to draw the root locus. So the root locus would be, based on the information that we have, we'll have the two, we'll have J omega imaginary and the real axis, and we see that the zeros, for the zeros we have Z is equal to 0.5. For the poles we have so the zeros here, so the zero will be around here, 0.5. For the poles we have S minus 3S plus 2, which is equal to S minus 1, S minus 2, which means the poles are P0 is equal to at 1 and P2 is equal, it's at 2. So we have a pole here at 1, we have another pole here at 2, and we can begin to draw the root locus here at the left side of an odd number of zeros and poles. We keep that, and here as well. So that would be the root locus. And then this one is similar to the previous one. We can calculate here the breakpoints. We can calculate the breakpoints of this root locus by noting that if we divide our transfer function, here we divide our transfer function, we say the numerator polynomial is s minus 0.5. The denominator polynomial is equal to s squared minus 3s plus 2. And then you can say the derivative of the numerator is going to be 1. And then the derivative of the denominator is going to be 2s minus 3. 2s minus 3. Now we know that in order to get the breakpoints, we have to substitute n of some sigma point derivative of s minus d of that sigma point, and then n of that sigma point is equal to 0. So this would give us the location of the break-in and breakout points. So if we substitute that n is this, so we have sigma minus 0.5 times d, it's 2 times sigma minus 3 minus d, here we have sigma squared minus 3 sigma plus 2 times the derivative, which is simply 1, is equal to 0, which means we have in this instance 2 that squared, and then we have minus 3 sigma minus 1 sigma plus 3 plus 1.5 because 3 times 3.5 is 1.5 minus sigma plus 3 sigma, what else is there, minus 2 is equal to 0, which implies that if you take the sigma squared, if you take this minus 3 minus 1 plus 3, that gives you minus 1, and then you have 1.5 minus 2, it's negative 1.5, and then if you take the roots of this, it means we have the breakout point at roughly 1.366 and negative 0.366. So which means we know that at 1.3 somewhere here, as well as negative 3 somewhere here, we have our breakpoints. And then we remember that the arcs are going to be circular. We can simply assume that we have the root locus like that, because it's symmetric, it will also go like that. One pole goes to infinity, another one goes to a 0. So we have our root locus here sketched, and then this point is going to be that, and this point is going to be this one. So we have a sketch of the root locus. Now we have just sketched the root locus. We need to find the values of k for which the model is stable. As you can see from what's happening here, is that as the value of k increases, the roots begin unstable, they move upwards. One of them will move upwards, and then it crosses into the stable region, and then another one will also cross into the stable region. And then as you increase k further, they remain stable for some time up until one of them crosses back into the unstable region. So there should be some value of k for which the poles are both in this region, which means they are all here when they're here, before they can cross back into the unstable region. So let's find out. With that, we can now begin to answer the question of how do you make the model stable, right? So in this instance, what we do, what values of k make the model stable? We see that there are 2 points where these changes happen. So first of all, we see the k will increase as initial stated. So the k will increase when the poles move from this side up until this point. So at this point, the transfer function becomes stable, right? And then what happens is this pole will then proceed again to move. Let's make it red. It will move like that, and then when it gets here, it also becomes unstable. So the range of k values that we are looking for are these k values that places this particular pole here in the left half plane, because it will move from the right to the left, and then as we increase k, it will proceed to move to the left and then come back to the right again. So now it means we have a value of k. We have both the upper limit and the lower limit here. So we have the upper limit and the lower limit of the value of k. The lower limit of the value of k is when the pole is at 0, which means one of the poles is going to be 0 at this point in time. And then at the lower limit, so at the upper limit, this is what's going to happen. So this will give us the biggest value of k. At the lower limit, we see this is at this point. So we can zoom and see what the value. We already know that the real part, that is the real part of the pole here, is going to be 0 because it's crossing the imaginary axis. So it's on the imaginary axis. So if we zoom in, as shown here, we zoom into that graph, we see that the 0, it crosses the pole at, it crosses the imaginary axis at about this value, which means the value there of the pole, it's going to be 2 conjugate poles plus or minus 0.707 J. So this gives us the lower limit. So we have got both the poles for the lower limit and the upper limit of k. So to calculate the upper limit of k, we know that k will be equal to the magnitude of this 1 over g of s, which is the magnitude of s minus 0.5 over s squared minus 3s plus 2. So here we know for the upper limit, it's when the pole is, for the upper limit, it's when the pole, or when s is equal to 0. So when s is equal to 0, we have 0 minus 0 plus 2 divided by 0 minus 0.5, which is the same as saying 2 over 0.5, which is 4. Now, it means therefore that the upper limit here, let me do it in black, it's 4. The upper limit of k is 4, so k cannot exceed 4. That's the maximum. Let's look at the lower limit now. If we look at the lower limit, which can be a bit challenging because now it has imaginary numbers, we will see that we need to substitute minus 0.707 j squared minus, so let's take for example, let's take the positive one, minus 3. So that is that squared minus, and then plus 2 divided by 0.707 j minus 0.5. So this is the substitution, and then if you calculate this properly, it will give you something like it should give you 1.5 minus 2.12J on top, and then you will get minus 0.5 plus 0.707J. Now if you multiply by the conjugate here on both sides, you multiply by the complex conjugate, then you should have a value like 2.3 divided by 0.75, which is approximately 3.0. So now we know it therefore means our values of K, it's going to be from the minimum, lower limit is 3, K, which is 4. So for values of K between 4 and 3, this system will be stable. One of the simplest ways to implement a controller is to use what's called the PID controller, the proportional integral derivative controller. This is one of the most widely used controllers in industrial applications, and it contains 3 terms: proportional, integral, and derivative. Sometimes it's called a 3-term controller. So each of these will contribute. If you look at the controller output, the proportional gain will contribute the control action that's proportional to the error, and then the integral will contribute the control action that's proportional to the integral of the error, while the derivative control we propose will contribute the control action that's proportional to the derivative of the error. The derivative controller transfer function is usually this particular one. KD over S is usually given with a small time constant tau as KD over S divided by tau S plus 1, where tau is much smaller than any other time constants of the process, so it's normally ignored. So KD, instead of just writing KDS, this controller is normally presented as KDS over tau S plus 1. So there could be multiple variations of this controller. One such can be, for instance, a proportional controller. When all other gains are 0 and only the proportional gain is being used, this becomes what's called a proportional controller. If the derivative gain goes to 0, or it's left to be 0, or eliminated from the controller, then this is called the PI controller. If the integral gain is left to be 0, then this can be called PD controller, or proportional derivative controller. So how then do you determine the values of K and D? Well, the root locus can be used as one method, and there are other multiple methods, which is manual tuning, or the Ziegler-Nichols rules of tuning. So the process of determining the values of the PID controller is called tuning. So in terms of the Ziegler-Nichols tuning, it's a rule-based tuning which uses the open loop response. So there are many variations which we shall not get into in this course, available in the reference text for those who would want to explore them. In terms of manual tuning, this is a trial and error process, and tuning is done gain by gain. Typically, you would set all these other gains, the integral and the derivative gains, to 0 whilst you tune the proportional controller first, and then after tuning the proportional controller, you tune the derivative controller, then afterwards you tune the integral controller. So it's a trial and error method, but the rules of thumbs remain that, for instance, increasing the proportional control, that is increasing KP, will tend to increase the peak overshoot with little impact on the settling time, but this will also decrease your steady state error. Whereas if the integral controller is increased, this will increase the peak overshoot like the proportional control. It will also increase the settling time. And the good thing about the integral control is that it has the ability to eliminate the steady state error instead of just decreasing it. Whereas the derivative control will tend to do the opposite in terms of peak overshoot by decreasing the peak overshoot and decreasing the settling time, and with no impact at all on the steady state error. So at this stage, we have tackled the root loss, the idea of a root locus, the concept of root locus, the procedure of how to construct root locus, or at least try to understand how the root locus is being constructed by a computer. And then we have looked at how to determine the characteristic equation and how to use that characteristic equation to use root locus analysis for our control systems. We have looked at sketching, deriving a sketch for a root locus, and just now we have just discussed the structure of the PID controller and what each of these terms, or the impact of each of those terms on the closed loop control responses. Go through the tutorial in order to practice some of the problems in order to grasp the concepts, and then refer to the end of book chapters. In this instance, we are referring to chapter 7 for the root locus and the PID, and chapter 11 for the section on state space control systems.